So we will go with this class. It doesn't seem that with the amount of time that we have left for the semester, we'll be able to cover this material, but I intend to continue after the semester is over until the material is finished. And if you want to, we can continue with it, right? Your goal is to understand the subject, not really the grade, correct? Yeah, so I intend to just go beyond the semester and finish the subject. How many of you would join if I continue doing so? Okay, one person. What about the rest? Yes. Make sure there is a correct answer here. You understand? Well, I mean, I want to finish this full sequence of lectures. There is chapter 6, at least part of it, right? And chapter 5. So I'd like to finish all of it, record it, post it, whatnot. So another thing is make sure that if you don't care for the subject, do not ask me for recommendations. That's my personal request. I have like 12 of them, right? And I hate writing recommendations. I don't know why people always ask me. I write always a good recommendation, but I mostly lie. Yeah, of course, I'll send you messages, right? And we'll see who is coming. All right, so let's go with this topic. So if x has a probability density function f of x, find the probability density function of y, where y is equal to 2x. Okay, let's see how we do that. Okay. So what we have is a probability that y is less than or equal to a. That's what we want, because if we know the cumulative distribution function for y, we will be able to recover the density function by taking its derivative. Do you remember? Fundamental theorem of calculus. The cumulative distribution of y is if you take the derivative of it, you will get the density of y. So that's the probability that y is less than or equal to a. But that's the same as the probability that 2x is less than or equal to a, which is probability that x is less than or equal to a divided by 2, which is simply the density for, the cumulative distribution for x evaluated at a divided by 2. You understand? Now I take the derivative with respect to a, and that would be the derivative of this expression with respect to a, and that would be 1/2 the density function of x evaluated at a over 2. So since I already know what is how s is distributed, right? So that means that it will be, well, I mean, actually I haven't mentioned here, so it will be the next question. Suppose x has the probability density function given by 1/2 if x is between 0 and 2. So 1/2 means what? It means that you can think you have a density function that's a horizontal line, which means that the histograms, or those boxes that build it up, are all of the same elevation, which means that every outcome is equally likely to occur, right? Every value of x has the same likelihood of occurring, or x is equally likely to occur in every sector between 0 and 2, no matter how small. Yes. So your goal is to find the probability density function of y equal to 1 divided by x. Do you understand what you want to find? So many continuous probability density functions are generated this way. You begin with one that you know is continuous, and then you know that the next one you generate will also have this property, right? It will just have a different shape. So you understand what we're asking for? We are asking for outcomes of the form 1 over x. So where x can be a number between 0 and 2, 1 over x will be the numbers between 1/2 and infinity. Yes? 1/2 and infinity, because take 1 over 0, it's infinity, 1 over 2 is 1/2. And so they're switched, right? the inequalities are switched when I take reciprocals, correct? So that's what I'm interested in, right? So naturally that some numbers are going to be more likely than others because certain parts, let's say parts close to zero, are stretched very far. Okay, so how are we going to do that? So how do we find it? So first we notice that if x is between 0 and 2, then y is between 1/2 and infinity, as I mentioned. Okay, so then we begin with the cumulative distribution and we make use of the fundamental theorem of calculus, right? So that's the probability y is less than a, probability that 1 over x is less than a. I can say less than because I can always downgrade between less than or equal and just simply less than because a will never occur. Or at least its probability of occurring is 0, to be precise. So probability 1 over x less than a is the same as the probability that x is bigger than 1 over a. Yes? And that is the same as 1 minus the probability that x is less than or equal to 1 over a, which is 1 minus the cumulative distribution of x at 1 over a. And then I simply take the derivative with respect to a. You understand why we take the derivative? I reviewed quickly the fundamental theorem of calculus here, yes? And the derivative is what? It's 1 over a squared. That's because the derivative of this thing is minus 1 over a squared, and there is a minus in front. So it will be 1 over a squared, the density of x at 1 over a. Good? And now I can simply plug in, instead of a, I can put in y. What will I obtain? This is always, whenever it's defined, it's equal to 1/2, correct? The function f for any number where it's defined is 1/2. So a is between 1/2 and infinity. And when I take reciprocals of it, right, well, reciprocal of a, that number is between 0 and 2. So that number will be equal to 1/2. You see that? So that would be 1 over y squared multiplied by 1/2 and 0 otherwise. Do you get it? Now here is your turn. This is your function. This is x. It has a cumulative distribution, well, a probability density function given by this formula. Your goal is to tell me what's the probability density function of y, which equals to e to the power of x. All right, let's do it together. All right, so here is the idea. Very simply, we are going to start with the cumulative distribution of y. Okay, so we are going to have f of y at a. It's just the probability that y is less than, or we can say less than or equal to a, it doesn't matter. Okay, for continuous distributions it never matters. So that's probability e to the x is less than a, because y is e to the x. Okay, and then that's the same as asking for the probability that x is less than ln a. By the way, the values, a is just some value that y can take. Now, because x takes the values between 0 and infinity, clearly a cannot be smaller than 1. Do you agree? Because e to the 0 is 1, and then e to the infinity is infinity, right? So you cannot have values smaller than 1 for y. So a is assumed to be a number bigger than or equal to 1. You can say always bigger than 1. So then we have we are interested in the probability that x is smaller than ln a. You see how I converted back to a? And that is simply the cumulative distribution of x at ln a, right? And what do we get? We get that when we take the derivative, we are getting derivative of capital Fx at ln a. It's 1 over a little fx ln a. Yes? Which is 1 over a e to the minus ln a. You see that? Why is that so? It's just derivative of the outer function is e to whatever power, right? And derivative of ln a is 1 over a. So it's just a chain rule. And then this is the same as 1 over a times 1 over e to the ln a, which is again 1 over a. So we get that the density function is 1 over a squared, which means in particular that, and I made a mistake, I believe. I wrote y is between minus infinity to infinity. I meant that y is bigger than 1. There is a mistake, typo, okay? This must be a y bigger than 1, because y is e to the power of x, right? And then you can verify that the integral from 1 to infinity of 1 over y squared dy, it equals to minus y to the minus 1 evaluated from 1 to infinity, which is simply y to the power of, sorry, it's simply 1 to the power of minus 1, which is 1. So that checks out. The integral of the density function has to equal to 1. And I, in my notes, wrote a mistake. You see, it's not minus infinity, it's 1. Good? Let's go on. So now we are going to talk about expectation and variance of continuous random variables, what that might be. So this is a very simple way of thinking of it. If dx is small, then x, and then the probability that x is between little x and x plus dx is approximately the height of this density function multiplied by dx. Do you understand why? We're presuming the function f is continuous, and so where dx is small, we essentially have a rectangle. It's a thin rectangle. That's basically, it was built out of rectangles. From rectangles you come, and to rectangles you go. Good? Everybody understands it? Really, what is the idea of this density function? It's really just the skyline. This is the curve is the skyline of those very thin skyscrapers that you see in New York, right? They're very thin, and each skyscraper represents the probability that x is in the base of that skyscraper. So if they're very, very thin, and there are many of them, that will be essentially what a continuous distribution is doing, okay? You're just adding all those many thin rectangles, which you approximate by integration. So then it is clear that the expected value of x is essentially what you can imagine, divide this number line into many small parts, and then you have lots of those x's at each interval, right? You basically have a billion skyscrapers here, and they will form the skyline, and each of them is a rectangle, and we just add over the possible values that can be taken. We can imagine them to be discrete. You understand what I'm talking about, guys? So if I were to zoom in and I were not precise, I can always imagine the situation to be discrete. So this is one x, here is another x, here is another x, here is another x. Here, of course, I made the gaps very wide. And what is the, let me actually clear it. Here is the idea. Here is that interval. And here we're making very thin rectangles, right? So you have here, let's say this is x0, this is x1, and in general, somewhere over here, we have xk, right? So we can imagine that the actual variables that the actual values that x can take is discrete. We can imagine that x equals to xk with probability f xk multiplied by dx. dx is the width. You understand what I mean? And so you just add those things up. dx, you can imagine it's just a Riemann sum. If you remember Riemann sum, so it's over k. And that simply translates to integral over this full interval, let's say from a to b, of fx dx multiplied by x. I forgot to put an xk here. Yes, xk times f of this is the probability here. That's the area of this box. So guys, it's always a delayed response. I see very few faces here for some reason, even though you are, I suppose, advanced students. Yes. So because I see a few faces, I do not know what's your reaction. Do you understand me or do you not understand me? So I hope I was able to explain very intuitively why expected value is defined as it is, right? It's defined to be the integral in general from minus infinity to infinity of x f of x dx. You know, I hope you understood why that's a valid definition. If the function is continuous, this x f of this x is it's like the discrete value that the random variable takes, whereas f of x dx is the area of the box corresponding to that x, and that will be roughly the probability. Okay, and in the limit, we think it's going to be approaching what we imagine the expected value should be. Okay, so here is an example. So find the expected value of x, where the probability density function of x is 2x if x is between 0 and 1, and otherwise 0. Can you calculate it without my help? Okay, thank you, Indrapret. So let's carry out this calculation. Very simply, it's just the integral from minus infinity to infinity of x f of x, which happens just to be x multiplied by 2x dx, where the interval is from 0 to 1. And that happens to be 2/3 the result, right? The integral is 2x squared, and that would be x cubed divided by 3 multiplied by 2, and the result is 2/3. Good, that's the expected value. So if you were to simulate generating those numbers, generate enough of them, the average will be 2/3. Good. Here is another one. So what's the expected value of e to the power of x, where f of x is 1, where x is between 0 and 1? What's the expected value here? Yes, Naomi, but the question is, you're sure you know that you did it right, right? So let's carry the calculation. Okay, we're actually going to do it two ways, and one of them is a bit more annoying, and the other one is very quick. So first, I am not given. You see what I'm supposed to do by definition of expected value. I'm supposed to find the corresponding density function, correct? F of x is this little f is the density function of x, not of e to the x. Good. So let me carry this calculation and see what I do. So I set y equal to e to the x, and then I try to calculate the density function. And I carry out this calculation that we already talked about. And I see that my density function is 1 over y, where y is between 1 and e and 0 otherwise. Okay. That's my, yes, my y can only take values between 1 and e. Good. You understand?
I have a question.
Yes.
I did it a different way.
I know.
But I don't know if it was just a coincidence.
It was not.
Okay, yeah. So if you set x equal to e to the x, can you just say the integral from e to the x times 1 dx from 0 to 1?
And that's the question, why can you say that? Right? That's what I was asking, right? So technically speaking, you have to be always careful, right? So yes, so notice what we got is, that's what I said, you do it this way. So I translated, first of all, to the density function of y and calculated the integral, and I see e minus 1 is the result, right? The expected value is e minus 1, okay? We will get there in a moment, just because, again, right, f was the density function of x, not of e to the x. So what I did here first is convert and create the density function for y, and then carry the integration. And of course, a good question is, do I need to waste my time doing it, right? That's a very good question, and we will return to that question shortly. Okay, here is another question, right? So here again, I am given the density function of x, but not the density function of root x plus 1, okay? So if I do it directly, first of all, I see what can y take. If x takes numbers between 0 and 1, y will take numbers between 1 and root 2. Agreed? So those are the values. And then I carry out the ugly calculation of the density function of y, which you understand how I do it, right? I just begin with the cumulative distribution of y, and then I convert it to the expression involving the cumulative distribution of x, and then I take the derivative. You understand how this process works, guys? Yes, and once I take the derivative, I obtain this very ugly function, and then I integrate it from 1 root 2, and once I carry the integral, I get some strange number, okay? And here is now, so guys, do I need to say more? You understand how what's the idea? The idea is that if you understand the fundamental theorem of calculus, you understand that cumulative distribution, being the area under the curve, relates naturally to the density function. So I can use that, that's why I understand why cumulative distributions are interesting for continuous random variables, but I don't understand how much why they are interesting in discrete random variables, right? Because here I use them as a tool to obtain density functions, to convert from one variable to another. Good. Now, so the question here is, do we need to do that work, right? Once we have, let's say, e to the x or root of x plus 1, those are random variables that are functions of my original random variable, right? For which I was given the density. So you see, so here is, I suppose, what Naomi did. Same problem, but instead of converting to another density function, just integrate over the density function of x from 0 to 1, e to the x dx. And the result is e minus 1, right? And I could have done the same thing perhaps with the second problem I presented, that of expected value root x squared plus 1. Simply integrate from 0 to 1 root x plus 1 times 3. It's not x squared, it's x plus 1. 3x squared dx. And then I carry out a bunch of u substitutions, by the way, arriving at a similar result, as you can see. 2 and 3, it's basically, I got that same, after u substitution, I got that ugly thing that I had before. Right? And in other words, the result is going to be the same. You see, for both of those questions, the result is the same, despite the fact that I haven't bothered converting to the density function of this new variable y. Okay, now why might that be true? You can actually think that it might be true already knowing the discrete case, right? So you understand, if you understand that continuous is just a sort of abstraction of the discrete case, you can see why that result is going to be true. It's just a rearrangement of sums. That's really all you're doing, right? Just like we remember how we were when we change one random variable to another, that's just rearrangements of the values. Just you're relabeling the values to be something else. Okay, that's why it's so good to understand what are Riemann sums, that they're just really additions, nothing more. Okay, so let me perhaps draw you a picture, and then we will talk about the rest here. Okay, so what do we have here? We have now a sort of, well, actually, since we're not doing it for several dimensions, let's imagine that this is our sample space. Okay, this is our sample space when it's a continuous distribution. But you see, I can understand much about the continuous distribution, but by imagining it's built of many tiny blocks. And a typical block is labeled as, well, this typical block has value, you can imagine its value x, and its probability of being selected is f of x dx. You understand what I'm saying, guys, right? So just the histogram that is, you can imagine it's not being drawn here, doesn't matter, right? F of x is a density function multiplied by dx, and you get the probability of that block. Where I imagine that there are just finitely many dx's here. I divided this into finitely many segments. So what is a variable x doing? Is just we have those values labeled here, right? Now, when I apply a function, some sort of g of x, I simply relabel a bunch of them, right? So a bunch of them are relabeled, and so I know that let's say the probability. So I know, for example, what is the expected value if I relabel them. Relabeling them, in other words, this is now labeled as gx. Yes, that's the value that you're adding. So what was the expected value before? The expected value before was essentially before it was this, right? X f of x dx. You understand? where f of x dx is just a summation of it. That's what it's a discrete situation. Now, what happens when you relabel them, right? You're getting just different scores. The scores were updated, correct? So what will you be getting? What scores are you getting? It's just instead of this x that you're multiplying by the probability, you are multiplying g of x. You agree? Because you have to understand what are you truly, that's what I mean when you think very simply, what are you truly doing? You truly can imagine when it's a continuous distribution, it's like you're summing, you're creating the average of maybe millions or billions of scores, right? But a billion score, which is very good approximation to continuity, is very similar to when you do it with 5. That doesn't matter, right? Just if you understood how expected value worked for the discrete case, you understand that like a continuous case is is well approximated by a discrete case where you have many instances, very many instances, like a billion instances, right? Or whatever huge number of instances will be a good approximation to continuity. You see that when you're watching movies, right? I'm watching you and you're so expressive and moving, but really it's just a 66 or something, let's say 60 frames per second, right? Or maybe a little more or a little less. But your videos that I'm watching is just lots of pictures, and that feels very continuous to me. You see, similar thing is here, right? If I divide the interval into sufficiently many segments, I will have a very good approximation to the continuous case. And I can, in other words, there is, for my understanding, there is only the discrete case, and I can kind of interpolate to more complicated cases. Are you with me, guys, or I'm completely missing you? Right? What do you do when you calculate expected value? You just have a new label for probability. Instead of p of x, you now have this value expressing probability. Yes, but the x here is just the size of the division. I partition this line segment into, let's say, billion partitions. Then dx is a billionth of this line segment. You understand? Yes. And so when I take expected value, I realized, I hope you remember that from chapter 4, you realized why that expected value was defined this way. It's always the particular scores that can exist multiplied by the probability. Yes? Shotaro, you're laughing. It means yes, you understand, or you're laughing like, well, I'm not making any sense whatsoever.
I mean, I think I'm getting it. Yeah, like it's area under the curve. We're just relabeling and everything, right?
The average, right? The reason it's area under the curve is because this summation, it's over kind of x, right? It's really just a Riemann sum for the integral from, let's say, minus infinity to infinity of gx f of x dx.
Yeah, so it's yes? That makes sense.
Completely. And everybody else, did I make sense to you guys? Right? If you think in terms of discrete, the discrete idea of area under the curve, then you essentially have a good understanding of what would be the continuous version of it. Yes? So here you have to have two things. You have to realize why expected value in the discrete case was what it was defined to be. The different values that the variable can take multiplied by the corresponding probabilities. And then imagine that what we do here is exactly the same thing. We just took those values. There are just many of them. If it's continuous, it's essentially like we have million or billion particular blocks, particular values that the random variable can take. Yes? And then simply when I apply a function g to it, I just relabel it. So that's why we were successful it's really just a matter of relabeling. That's why we were successful, well, Nomi in particular was successful in calculating the expected value without changing the function f. Yes? Of course, you do have to be careful. There is always a curved ball, right? So this works under the assumption that values can be rearranged. You see, it's because when you switch to a different random variable, you're creating rearrangements. Okay, so here I tried to give you a proof. You can read it if you want to. It involved, in fact, two variables. So here I kind of go and describe it using several variables, whatever happens, and all sorts of labelings. And so I use calc3 in my notes. You see that? So that's when you present the argument in whatever change of variables, blah, 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 right? Change of bounds of integration. But at the bottom, you see, if you're able to think in discrete terms, then you can come up with not rigorous arguments, but very plausible arguments. In other words, you are certain that you are not making a mistake. You're certain that you are right in all normal kind of everyday situations. But you might say that somebody might object to the proof. Okay? But the same can be said about changing the bounds of integration. If you take deeper analysis, if you take calculus on manifolds, which I also want to teach, that would be, you can see all sorts of kind of sick examples, perverse examples of where things do not work as you like. Right? And I love perverse examples because they confuse people. Good? So this is what essentially it should be, right? The expected value of g of x, you can still use the original distribution. I hope you understood, guys. Let me know if you did. It's an important milestone. Confirm if you understood the explanation I did on a very quick one. You can read this afterwards if you want. Good. All right, here is a question. A stick of length 1 is split at a point x that is uniformly distributed over 0, 1. Determine the expected length of the piece that contains the point t. You understand? So there is a stick, and on the stick there is a particular marking. You can imagine, you can draw it, right? So this is the stick. And somewhere on the stick there is a mark, point t. And the split is happening somewhere. I'm not sure where. Right here is the where the split is happening, and you have to determine the expected length of the stick that will have the point t. So if the split happens here, then that is the length you are measuring. If the split happens to where the cut is happening to the right of t, then it's the left piece that you're measuring. Melissa, by the way, were you able to understand what I said? All right, let's do it together since we don't have too much time. So here is the situation again, right? So there is a point T somewhere, and at some point randomly you will cut this stick. Good. So the fact that the density is 1, it means that every region is equally likely, because you understand when you say density is 1, it means the skyline is of skyscrapers that are of identical height, which means that if you give them the same base, if you cut, let's say, this interval into 1,000,000 pieces, then you have million skyscrapers that are twins, all of them, right? And that means each region is equally likely. That's basically the general situation for randomness. Good. General situation for randomness. So what is the function that I'm going to use? So the length of the stick at point X. So clearly that will be 1 minus X, because the length of the stick is 1. If I cut to the left of T, and then I have to take 1 minus the cut, because that's the right segment that I measure its length, correct? And the measure of the right segment is 1 minus the point of the cut. So like in here, right? 1 minus the point of the cut is where the T is located. But if I am to cut above T or to the right of T, that will simply be X minus 0 or X, right? So that is my function. Good. And because of what Naomi observed, and because of what we hopefully all observed when I explained it quickly, without, by the way, using Calc 3. Right? I do have that explanation here with Calc 3. Huh? Double integrals and whatnot, right? But so make sure to not miss it. It's like another sort of cookie. So what happens here is that the expected value, it's simply the integral. This function is piecewise, right? It's the integral over this density function from 0 to T, and then plus T to 1 of the value multiplied by density. And when I carry out this integral, I get, I believe, 1/2 plus T times 1 minus T. You can check if I'm right, okay? You understand? I just integrate it, simplify, and I get 1/2 plus T times 1 minus T. And this is maximal when T is equal to 1/2, because this quantity is maximal when both are, by symmetry, you might imagine, when T is 1/2. Okay, so that would be the maximal length if I select a point T in the middle. And this is a silly example of how that idea is used in optimization. So let's say that we know that there is a certain highway, and the place where an accident occurs is a random variable X with a probability density function equal to 2X between 0 and 1 and 0 otherwise. And now, where should the hospital be placed to minimize the distance traveled to from the place of accident to the hospital? You understand? So a sort of like civic engineering type of question. So we want to place a hospital or some sort of medical center over this highway, which I normalize to be from 0 to 1. And we have information on which places the accident is more likely to occur. So the accident occurs so basically the accident becomes, it's very likely to occur near the point 1. You see, more likely than near other points, because the probability skyscrapers are tallest near 1. So the question is, where should I place a hospital so that the distance to that hospital is shortest from the accident, the expected distance, naturally, right? So yeah, you can just set it up, and then we will do the integration and everything else together. All right. How are we doing? Ready? Yeah. So basically, if you haven't heard, I do plan to, first of all, extend the teaching through the finals week, since your final is a take-home, to cover this, and then possibly beyond the grading period to cover all the material. And naturally, I hope you will join. All right, let's carry the calculation. So here is the idea. So Q is the place where hospital will be built. And so what is going to be the distance to the hospital from the accident? If accident occurs in position X, then it will be Q minus X if accident occurs closer to 0 than Q, and X minus Q otherwise. Agreed? This is just absolute value of Q minus X split around whether X is to the left or to the right of Q, correct? So then the expected distance to the accident is going to be the integral from 0 to Q of Q minus X times 2X plus integral from Q to 1 of X minus Q times 2X. And when I carry out this integral, I carry it out, I calculate, I simplify, I will get that the function is, I call it E of Q, expected Q, so that it's shorter. It's a function of Q. It's going to be 2 over 3 minus Q plus 2 over 3 Q cubed. Yes? 2 over 3 Q cubed. And so then I go through the Calc 1 optimization procedures. Yes? So I'm optimizing cubic. I want this to be the minimum. And so I take the derivative of e to the q, right? I set it equal to 0. And what you have is that q ends up being 1 over root 2. The other one is minus 1 over root 2, but we are not going to go there, right? I mean, I'm going to put it just as a mark, but I'm going to build the hospital basically in between 0 and 1. That's my assignment. So I'm not going to build it at minus 1 over q. And besides, it's a local maximum. Okay, and then I see how the derivatives behave. The derivatives are positive all the way until minus 1 over root 2. They are negative between minus 1 over root 2 to 1 over root 2 and positive afterwards. So I see that my minimum is over 1 over root q. Agreed? That's my minimum. So that means that's where the expected value is smallest. That means the expected distance is minimized. I will build my hospital at position 1 over root 2. Good? And this is a very German problem. Germans cannot stand when you are not on time. If you are S minutes early to an appointment, you incur a cost of C times S. Right? So C is the price of being early times the amount that you were early. If you are S minutes late, the cost is K times S. So the cost is different for being late than it is to be early, possibly. That's why there is a C and there is a K. Okay? Now, there is a travel time to destination that is a continuous random variable with, it's a T with probability density function F. you see, your commute, you don't teleport. That's how you know it's continuous, Shotaro. Remember, you asked me, right? So the reason I know the travel time is continuous because you haven't learned to teleport. So your position will change gradually. Yes, that's how I know it will be a continuous random variable. And the density function will be some f. I do not know it, perhaps, right? And then the question is, at what time should you depart to minimize your expected cost? When should you leave? Given that this is an abstract question, and you solve it naturally just in symbols. Okay, so we will do it together because not too much time. Okay, so let D be the time of departure before appointment. You understand? So I'm going to depart at some moment D, and this is my appointment. Now, the cost that I will incur when I depart at time D will be what? Will be the early cost. The early cost is if I arrive before the appointment, right? If the time at which I arrive, T is the time of the time it takes me to travel. Okay, T is the time it takes me to actually travel. Okay. So this T is the time of travel to the destination. You know, sometimes it takes 1 hour, sometimes 40 minutes, sometimes 2 hours or something like that, right? And anything in between, or maybe sometimes 3 hours when there is a major slowdown, right? So when you enter in Manhattan or you enter in New York, there is major slowdown when it's not the weekend, for example, or accidents or whatnot, right? So so what you have is, you have C times D minus T if T is less than D. In other words, if the what should I say? Before appointment. So this is basically, D is how much time you have before appointment, to be precise. You understand? D is how much time you have until the appointment is scheduled. So if the time traveled is less than the amount of time you are allotted, then you incur an early cost. And if T, the amount of time you will travel, is bigger than the amount allotted, then you will incur a late cost. Do you understand me, guys? So just to be sure that my notes are making sense, yes? So then what's the expected cost that you will incur? So you have this integral, and I label this integral as expected value of D. Good? So let's look at it. So when I break it apart, and I take its yeah, so you see what I have here is I take the derivative with respect to D. Notice that this is just the derivative here with respect to D. It's a product rule. You understand? D is your random variable. So I take the derivative and I relabeled what it is. You see, this is the cumulative. This is the cumulative distribution here, right? So here I take the derivative of D and I evaluate this integral, and this integral is the cumulative distribution. Do you recognize it? Because the amount of time you travel is never zero. So it's between 0 and D. So this is the cumulative distribution. I calculate all that thing and group like terms to like terms. And I observe that, that the derivative is this expression. It's just product rule and the rearrangements and relabelings. And it is reducible to this situation. It's reducible once you look at it and simplify. It's reducible to C plus K times cumulative distribution at D minus K equal to 0. And so the 0 that you have here, cumulative distribution is always increasing, by the way, right? So what you have here is that the 0 is given when f of D is equal to K divided by C plus K. Okay, and if you select something before, you will have, if f of D is smaller than that value, it will be negative. If it's bigger than that value, it will be positive, which means that here is where it's minimized at k divided by c plus d. So the answer here is you should leave if you know if you know this random variable, how long it takes to travel, because you have statistics or because Google estimated it, whatnot. You should leave at a time d when the cumulative distribution is equal to the cost of lateness divided by cost of lateness plus cost of being early. Assuming, of course, you can make such costs and estimate them correctly. Otherwise, this is just a meaningless problem. Right? Okay. Here are some corollaries. If a and b are constants, then the expected value of ax plus b is a expected value x plus b. So expected value is a linear function, right? It has this linear property of being of going through. If you talk to linear algebra, you know what I mean. And here is a very simple proof of it. The expected value of ax plus b is just the integral of ax plus b times f of x dx. And integrals are just additions, right? So if there are just additions, it's obvious that you can rearrange them. Yet? You see, this thing, this s is just a sum. You understand? You're just adding lots and lots of terms. So when I think of integrals, and I don't have to be especially worried about whatever dangers might be with continuous functions and all those paradoxes. In essence, I'm just seeing, instead of an infinite addition, I'm seeing an addition of really many terms, of maybe billions of terms. And then I can just quickly, obviously, see that I can rearrange the summation and do it like this. Yes? And that is and what is this? This part is b multiplied by 1, because the integral from minus infinity to infinity of a density function will just give you 1, because that gives you the totality of possibilities for the random variable x. And you have the result. Yes? Now you might already obviously notice that variance should be defined in the same way as it was for discrete random variables, and that would be, if I know the expected value, x minus mu squared, take the expected value. Nice, I see a cat. So the expected value of that will be variance. Good? You understand me, guys, right? I'm not just mumbling something in my nose. Yeah, I hope. I mean, I do not know how you listen to me, but I hope it's better than I imagine what it is. So here is an example. So here x equals to some random variable that takes values between 0 and 1, and it has a density function 2x. Please help me and calculate the expected value of this random variable and its variance. Go ahead, calculate fast. All right, let's go. Ready? So very simply, we calculate the expected value of x and that of x squared. So the first will be 2/3, the second will be 1/2. Yeah? Because what I do, x squared, I take the density function multiplied by x squared and I integrate to x cubed. And then I just write 1/2 minus 2/3 squared and I get 1/18. That's variance. Simple. Wonderful. We finished with this lecture note and let's go to uniform random variables. So the most basic continuous random variable is the uniform random variable. And its distribution is simply that it's just a rectangle from A to B. Now, what should be the value of C, guys? So if the random variable x is uniform, it has a constant density function and it takes values between A and B. What's the value of C, please, very quickly? You don't need to integrate, right? It's a rectangle, right? What should be true about the area of this rectangle?
I mean, it's just B minus A times C, right? The area underneath.
Yeah, so C is simply 1 over B minus A. Yes, because the area has to be equal to 1. My God, I'm losing people by the minute. Like there were 13, 15, 13, and now I have 12. What's going on, guys? You don't like integrals? So then, what is the cumulative distribution? Well, very simply, we just integrate to find what it is at some value t. We just integrate from minus infinity to t f of x dx, which is integral from a to t, because that's the first time we have a non-zero values, from a to t, 1 over b minus a dx, which will simply be t minus a over b minus a. And so this is my cumulative distribution. It will be 0 until I reach a. It will climb linearly until I get to 1 at b. So from 0 at a to 1 at b, and continue to be equal to 1 all the way through. You understand? Because then when you're asking what's the cumulative distribution, it's always defined. Cumulative distribution is defined for all real numbers. You see why? Because it's 0 when the variable cannot take any values, and it becomes 1 once you already gathered every values that this random variable can take. Good. So now notice that. Of course, because it's a giant rectangle, there is no reason to use integration to evaluate probabilities here. Notice that if x is uniform and I is an interval or anything that you can measure length for, that's contained in AB, the probability that x is in I is just the length of I divided by length of AB, which is length of I divided by B minus A. Do you see that? Right? Because what do you really do? You just you measure what truly happens here. The reason you divide by b minus a is you measure the relative length. X minus a is the length, or just any probability that you would calculate here from any alpha beta. It will be, the integral will end up being beta minus alpha divided by b minus a. That means that your probability is just the relative length of the interval inside of AB. Good. So that's what's the idea. So here, let's calculate a few examples. We will finish 10 minutes later because many of you arrived 10 minutes late. That's the punishment from the previous problem. So x is distributed between 0 and 20. What is the probability that x is between 5 and 10? And what's the probability that x is bigger than 5? Please calculate it very fast.
Professor?
Yeah.
For A, would that be 1/4, and then for the second one, 3/4?
Well, let's see. So yes, they're obviously related, right? So so first of all, this is the length here is 5. The interval is of length 5. The full interval is of length 20. So we have 5/20, which is 1/4, right? Which you can of course carry the integration and you have it. You understand? It's pretty obvious because if all the skyscrapers, I call them skyscrapers, if all the bars are of the same elevation, all that matters is the width, right? So yeah, so the probability is just how wide is the interval compared to the full width. So we have 1/4 for A and 3/4 for B. Very simple. You agree? Now here is another question. Let's see if you can help me with this one. Theta is uniformly distributed from 0 to 2 pi. Compute the probability that sine of theta is less than 1/2. Right, so we select a random theta using the uniform distribution. What's the probability we will obtain sine of theta less than 1/2? All right. How are we doing? Simply ask yourself, how can sine of theta be less than 1/2? So first, if it's in the first quadrant, yes, in the first quadrant, and well, we're allowing negative numbers, right? So when is it less than 1/2? All the way from 0 to pi/6. Yes, sine is growing, right? 0 to pi/6, and then we have in the second quadrant, and then yeah, so we can do this. Okay, so sine of theta is, we can do it this way. Instead of calculating sine of theta less than 1/2, maybe easier to calculate sine theta bigger than 1/2. Okay, so if it's bigger than 1/2, it's that, so that we don't have separate pieces, right? Then we have from pi/6 to 5 pi/6 to the in the second quadrant. Make sense? And so what's the size of this interval? The size of this interval is 4 pi/6, and we need to divide it by the size of the interval, which is 2 pi, to get a probability. So it's 4 pi/2 pi and divided by 6. So it's really the same as 2/6 times 1/3, which is 1/9. Yeah. So the answer is did I make a mistake? So yeah, so this is one. So the answer is, sorry, 2/6, which is 1/3. So the answer is 2/3, right? The answer is 2/3 because I take 1 minus it. Good. All right. So here is one more question, and then we can maybe call it a day. So trains run every 10 minutes. We have 2 to 10, etc. If you arrive at a station at a time distributed uniformly between 2:05 and 2:35, what is, so those are kind of very regular trains, they run very well. right? So you arrive between 2:05 and 2:35. What's the probability you will have to wait under 5 minutes? Understood? The question understood? What's going on, guys? So very simple, right? So we have what before 10, 5 minutes, right? Before 25 minutes and before 35 minutes, yes? And then yes. So let's see here. So I said it this way: x is a random variable, uniform, where x plus 5 is the moment you arrive. Okay. So x is uniformly distributed from 0 to 30 because you then arrive. X plus 5 will then be uniformly distributed from 5 to 35. Yes. So so then we have this possibility, right? So we have x plus 5 is between 5 and 10, x plus 5 between 15 and 20, between 25 and 30, right? Good? Between 25 and 30. And did I miss?
Why don't you include the intervals of like in between 10 and 15 and 20 and 25?
Because then you wait longer. Because the train arrives only at the between 10
every
and
10
15,
minutes. Okay.
You missed the train.
Yeah.
You have to
Sorry,
wait yes.
I had every 5 minutes in my head, but it was every 10 minutes.
No trouble. Right. So yes. So we have this situation, and the thing is, I might have doing yes. So x plus 5 is between 25 and 30. Yes, right? Because then if it's 30 and 35, I wait longer. So those are the 3 intervals. Good. And they're all of the same exact length. You agree? So it's really 3 times 1 such interval. And that would, one such interval has length 5. And I take 3 times 5 divided by 30, which is the length of the time of my distribution. And the answer is therefore 1/2. Understand? Next paradox will be very interesting, but I'll let you go since have you heard the pleading cries of the cat? Yes. He really wants to. He looks at me. He tries to open the door, wants to leave, but I'm not helping him. So I imagine you feel the same way. And if so, have a good day. I'm stopping the recording.